Dynamic equilibrium. Chemical systems in balance and introduction. Here are some terms we need to be aware of. A reversible reaction is a chemical reaction that proceeds in both forward and reverse directions. Forward direction. In the forward direction, reading the reaction from left to right, the reactants form products. In the reverse direction, reading the reaction from right to left, the product decomposes to reform the reactants. A reaction where the reactants form products which react together to give the reactants back so that we have both forward and backward reactions is called a reversible reaction. Here is an example. Ammonia production is a reversible reaction. It has both forward and reverse reactions. Here is the equation. Notice the double arrow in between the reactants and the products to show that it's reversible. So what happens when 1 mole of nitrogen, N2, in the gaseous form, is added to 3 mole of hydrogen, H2G, in the closed system? In the closed system, energy can cross the system boundary, but matter cannot. Initially, the concentrations of nitrogen and hydrogen are high, and the concentration of ammonia is 0. This is shown in the diagram. As the reaction proceeds in a forward direction, the concentrations of nitrogen and hydrogen decrease, and the concentration of ammonia increases. Notice that to the right of the dashed line in the graph, the concentrations of substances no longer change over time. Remember that the reverse reaction is occurring simultaneously along with the forward reaction. Some of the ammonia is decomposing and reforming the reactants. The portion of the graph to the right of the dashed line represents a chemical system in equilibrium. Equilibrium, or plural equilibria, occurs when opposing forces or processes are in balance. In the chemical system, when the forward reaction and the reverse reaction are balanced and the reactions are occurring at the same rate, the system is said to be in chemical equilibrium. This chemical system at equilibrium has the macroscopic property of constant concentrations of the reactants and product. A macroscopic property is an observable or measurable property such as concentration, color, temperature, pressure, and pH. When the system is changing at the molecular level, but its macroscopic properties remain constant, the system is said to be in dynamic equilibrium. In the chemical equilibrium system involved in ammonia production, the system looks static because the concentrations are constant, but the system is dynamic because the molecules continuously react to form products and decompose to form reactants. Dynamic equilibrium, then, is defined as a chemical system at equilibrium that is changing at the molecular level while its macroscopic properties remain constant. So how do we write an equilibrium equation? Chemists use a simplified method for writing equations for reversible reactions like the one that produces ammonia. Chemists combine the two equations that represent a reversible reaction into a single equation, such as this one. Reading the chemical equation from left to right shows the forward reaction. Reading the chemical equation from right to left shows the reverse reaction. The double arrows indicate that the chemical reaction is proceeding in both directions. In an open system, shown in A, water molecules vaporize and escape into the room. If the system is closed with a stopper and air is removed from the flask, which is shown in B, water vapor cannot escape into the room. Over time, as shown in diagram C, equilibrium occurs between the water vapor molecules and the water molecules. A plot of vapor pressure versus time under constant temperature, shown in D, shows that at equilibrium, the rate of vaporization equals the rate of condensation. The system is in dynamic equilibrium because at the molecular level, the system is constantly changing, as shown in this diagram. So let's look at the conditions necessary to establish equilibrium. In order for a system to reach equilibrium, the system must be a closed system. So what are the thermal energy requirements of a reversible reaction? So let's consider these thermal energy requirements. In a reversible reaction in which the reaction in one direction is exothermic and the reaction in the opposite direction is endothermic, changing the temperature alters the rates of the forward and reverse reactions. A temperature increase adds thermal energy to the chemical system. Additional thermal energy causes the reaction that absorbs thermal energy to proceed at a faster rate than the reaction that releases thermal energy. The rates of the forward and reverse reactions are no longer equal. The opposite is true if the temperature is lowered in the chemical system. When the temperature decreases, thermal energy is removed from the system. When thermal energy is removed from the system, the exothermic reaction proceeds at a faster rate. Because the rate of the forward reaction and the rate of the reverse reaction are no longer equal, the system is no longer at equilibrium. Systems in equilibrium, then, can be classified according to the components in the system. They can either be homogeneous or heterogeneous. So let's take a look at homogeneous equilibrium. This is a chemical system in equilibrium in which all the components are in the same physical state and is known as the production of ammonia represents this type of equilibrium because all of the components are in the gaseous state as shown below. A heterogeneous equilibrium is a chemical system in equilibrium in which the components are in different physical states, as shown below. Note, the components in heterogeneous equilibrium do not have to be the same substance. For example, in the system where limestone decomposes and forms quicklime and carbon dioxide, heterogeneous equilibrium occurs. This system represents heterogeneous equilibrium because the system contains two components in the solid state and one component in the gaseous state, as shown in the equation. Common factors in the equilibrium system. A system is in equilibrium when the rate of the forward process equals the rate of the reverse process. The macroscopic properties such as color, pressure, concentration, and pH of an equilibrium system are constant. At equilibrium, there is no overall change in the properties that depend on the total quantity of matter in the system. Equilibrium can only be reached in a closed system in which matter cannot cross the system boundary. To establish true equilibrium, a system should be a closed, isolated system in which neither matter nor energy can cross the system boundary. However, small changes to the components of a system are sometimes negligible. So equilibrium principles can be applied even though the system is not completely closed and isolated. Equilibrium can be established from either direction. For example, in the reaction previously shown of the decomposition of limestone to quicklime and carbon dioxide, equilibrium can be established regardless of whether the reaction starts with only reactants such as the limestone or with only products such as quicklime and carbon dioxide. Coming up next, the equilibrium constant expression. Please join me.